All right, remember we're learning how forces relate to energy and momentum. The work energy theorem relates the energy of an object or system to the work done on the system. The initial energy plus work equals final energy. Remember, we've kind of done this before, where we did our conservation of energy, and we said the energy in the beginning equals the energy at the end plus thermal energy. This is the same kind of idea, except work is not a type of energy. Note that this follows the pattern, what an object had plus what an object got equals to what the object now has. Here's a short proof showing how work adds to an object's kinetic energy. So starting with the no-time equation, we have v squared equals 2a times x plus v naught squared. And then if we multiply all the terms by 1/2 m, then we now have 1/2 mv squared on the left. The 2 goes away, and we're left with mass times acceleration. Oh, mass times acceleration! That's the same as force. Oh, look even further. We have mass times acceleration times displacement, which is force times displacement. So reading from right to left, we have the kinetic energy that the object starts with plus the work done on the object equals the kinetic energy the object ends with. The impulse momentum theorem. Two theorems, impulse momentum and the work energy theorem. A word about the work energy theorem. I like to think about the work energy theorem as a bridge between forces and energy. So this is the only way where you can incorporate forces and deal with energies at the same time. So if you're dealing with a problem that's talking about forces and it's got a height and a velocity, well, we can use the work energy theorem to kind of figure some things out there. So keep that in mind. Work energy theorem is the bridge between forces and energy. The impulse momentum theorem, this is the bridge between momentum and forces. A force takes time to give or take momentum. Impulse is a transfer of momentum. Because momentum is conserved, if an object or system undergoes a change in momentum, another object or system had an equal but opposite momentum change. For example, if a car gains rightward momentum, something else lost rightward momentum or gained leftward momentum. Only a force can transfer momentum. The amount of momentum transferred is called impulse. Because impulse represents a transfer of momentum, impulse is measured in the same units, kilogram times meters per second, as momentum, right? Momentum is mass times velocity. These units are equivalent to Newton times a meter. If a force F acts on an object for a time delta t, then the impulse is calculated by the equation change in momentum equals force times delta t. Impulse is a vector because momentum is a vector. A rightward force causes a rightward impulse. A leftward force causes a leftward impulse. The impulse momentum theorem relates the momentum of an object or system to the impulse applied to the system. We have our initial momentum plus the impulse equals our final momentum. This is the bridge. Impulse equals force times delta time. This follows the pattern. What an object had plus what an object got equals what the object now has. Here is our proof, starting with velocity as a function of time equation. Multiply each side by mass. And we get mv equals ma times delta t plus mv naught. ma, there's force. So we're left with mv equals F times delta t. So we see, reading right to left, momentum of an object starts with plus the impulse applied to the object equals the momentum that the object ends with. The impulse momentum theorem and work energy theorem are shown on the AP physics equation chart. Here's the impulse momentum theorem. Change in momentum equals force delta t. And here is our change in energy equals work done, which equals the parallel force times displacement, equals FD cosine theta. We haven't talked about the FD cosine theta part of it yet, but we will later. Here are some examples.